Ladies and gentlemen, hello and welcome, coming to you once again, not quite live, from One Take Studios, where we are talking about radical expressions and rational exponents today. If you're not paying attention, those words just kind of blend together, so please make sure that we understand what we're talking about. Radical, that's like radical signs, square roots, cube roots, fourth roots, all that kind of fun stuff. And then rational, again, ratio, we're talking things that have fractions. Ooh, fractional exponents, rational exponents, that's going to be interesting. Okay, so for starters, we're going to do a little bit by way of review, just real quick. What are our properties of exponents? I want to run through, I think, 5 or 6 of them right now. So again, this is review. This is not an original introduction to properties of exponents. One of our properties says that if I'm multiplying and I've got an exponent for that product, I can take and apply that exponent to each of my factors. So a times b to the n becomes a to the n times b to the n. As always, properties are not one-way streets, they are two-way streets. So that also means if I see something like this, where I've got two different bases but the same exponent, I can condense it this direction as well. I am leaving a space here on purpose because there's something I'm going to slide into that spot. The next property up is going to be this one right here, very, very similar. If this works for multiplication, it also works for division, because division is just an alteration, another form, another way to look at multiplication. So same kind of thing. If I'm dividing and I have an exponent, that exponent applies to both the numerator and that denominator. So there's property number 1, there's my bullet point, there's property number 2, there's my bullet point. Please understand that you will only see these properties for multiplication and division. This is not true with addition and subtraction, hence those properties don't exist. Alright, again, I am leaving a gap because there's something I'm going to fill in there to go with that. I'll come back to it. Next property is a to the m times a to the n. Please notice it's not the same as what we have right here. Here we had two different bases but the same exponent. Here we have the same bases but different exponents. If I am multiplying with the same base, how does that work? I keep the base and add the exponents. So there's our next property right there. Keep the base, add the exponents. Next one up here, again, very similar to the previous one. If I've got a to the m over a to the n, again, this time I'm dividing, but it's the same base. What do I do with the exponents? Well, if multiplying is adding, then dividing must be subtracting. Somewhat logical, definitely a pattern there. Alright, and I think, yeah, this is the last property I've got. So 5 properties for today. A to the m to the n, if I'm multiplying, if I'm taking something to a power, I'm multiplying it times itself, which means essentially I'm jumping back to this property. I end up multiplying my exponents right there. So keep those in your mind. We're going to be using those. A lot of people are like, yeah, I know what those are. Trust me, you probably don't use them correctly. Alright, now, to fill in the blanks back here, something else I want to go back to. Again, it's something I've mentioned in a previous video, so I'm not doing a from-scratch introduction here. And that is this idea right here. Dun, 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 dun. Okay. A rational exponent is a radical. There's a reason these two things are in the same sort of discussion here. Alright, a rational exponent is a radical. In other words, rational, fraction, if I have a base with a fraction for an exponent, the top number is the power and the bottom number is the root. In other words, this is a root, this is a radical, even if it looks like an exponent. By way of an example, let me show you this. Let's say that I've got x, and I've got x to the 2/3 power. X to the 2/3 power, well, that is a rational exponent. And that's my base, so this is power over root. The top number is the power, the bottom number is the root. So what is this saying? What's another way that I could write this? Well, if 3 is my root, this is the third root of x squared. Power over root. 2 is the power, 3 is the root. If you don't like that, very, very similar to that, you can also go cube root of x squared. There is no specific order of operations here. As far as if you want to do the power first or the root first, it doesn't matter. You're going to get the same outcome regardless. What does this mean about our properties of exponents? It means that they also apply to radicals. So 2 of these I'm going to kind of convert to a radical format so that we can see it. But another one of our properties here, so technically this is, I suppose, a property of radicals? Sure, why not? We're going to call this the nth root of a times b, the nth root. Please understand that so many people work with square roots, they don't even realize that a number might go on the outside. Square roots are just the tip of the iceberg. You can do cube roots, fourth roots, fifth roots, whatever root you want. But what does this mean is going to happen? If a root is really just the same as an exponent, then this is going to apply the same way. This can be separated and called the, wow, that's not an n. It can be called the nth root of a times the nth root of b. Nth root of a times the nth root of b. And again, strong reminder, these properties go both directions. In other words, if I have two of these, I can actually combine them into one radical under the same radical. All right, and then partner for this guy right here is going to, again, be very similar. If this works for exponents, it also works for radicals. So if I've got a over b, but I have the nth root of a over b, very similar to the last one, I can split that, and I can call that the nth root of a over the nth root of b. All right. That's it. Again, very similar to that property that we see for exponents. It's just with radicals, we can do this because exponents and radicals really are the same thing, two sides of the same coin. Okie dokie. So that's our basics. That's our groundwork. Everything else today is just practice, the nuts and bolts. We've got even no application with this. The only way to get better with these ideas is to actually work with them. And many people think they have it down. They never look at these things. They make all kinds of mistakes left and right. So I just want to kind of send home a couple of messages to your brain that get overlooked. We are going to be doing some simplifying, and here is our first problem right here. We're going to simplify the fourth root of 81x to the 12th. The fourth root of 81x to the 12th. Well, how does this tie into all of this stuff right here? We have rules for simplifying radicals. Quite frankly, I'm not entirely sure who made up those rules. I'm really not. Part of it I'm pretty sure had to do with back in the dark ages before there was technology, and you used to have to look up radicals and things on tables, and some of these formats worked better for tables. We have technology, so I'm not entirely sure why we're using all of these, but it does give us a really cool chance to work with some of these properties and see them in action. So rule number one for simplifying radicals. You may not have any perfect squares under the radical. Why do I have squares in quotation marks? Because that's so limited. This is how a lot of people learn it, but they're only working with squares, and then their radicals happen to be square roots. Let's expand our horizon, shall we? I can't have any perfect squares under a square root, but I also then can't have any perfect cubes under a cube root radical. And I can't have any perfect fourths under a fourth root. And that is where we are at the moment. We cannot leave any perfect fourths under this fourth root radical. What might that look like? Well, I have something that looks sort of like these guys, and what I'd like to do is take and split this into a couple separate parts to see what I can simplify. So I might do this. I might call this the fourth root of 81 and have that times the fourth root of, you know what? Hold that thought. The fourth root of 81. Why am I okay with this? Because believe it or not, 81 is a perfect fourth. 3 times 3 is 9, times 3 is 27, times 3 is 81. So this is a perfect fourth. So what if I use this property to separate our different perfect fourths? 12 has a perfect fourth, does it not? Couldn't I separate my x to the 12th and put x to the fourth here? Because the fourth root of x to the fourth, that's kind of nice. I can do something good with that. And then I can do another one of those, the fourth root of x to the fourth, because how many x to the fourths can I make before I have x to the 12th? Well, right now x to the fourth, that's x to the 8th. I can do one more of these guys. And this happens to work out really nicely for this example. Not for everything in life, but that's okay. So if I'm looking at this, I've used this property to kind of separate a couple things. X to the fourth times x to the fourth times x to the fourth is x to the 12th. Thus says my property, where to go, right here. All right, so I'm using this property. But then I'm using it with this to see what I can break down. I can take the fourth root of 81, so I will. That's 3. I can take the fourth root of x to the fourth. That's x. The fourth root of x to the fourth. Also x. The fourth root of x to the fourth. Also x. Ladies and gentlemen, simplify that. 3 times x times x times x is 3x squared. That is the simplified version of this right here. Now, can I show you something that maybe some of you caught on to right here? If we talk about power over root, let's look at just the x for a second. Power over root. That's x to the 12th power. It's a 4th root. You let me make that mistake, didn't you? Did you catch it? You better be yelling at me. Why did I write a 2 there? 3. There we go, 3x cubed, because x times x times x is x cubed. Okay, so much better. Now, back to what I was saying. Power over root, 12 over 4 is 3. So that's another way to view this for simplifying. And it works well with this because this happens to be a perfect fourth. Of course, that's not going to work with everything, but it's another way to view things and kind of check them out. All right, so again, we are just working with multiple properties here, trying to work on our practicing of these skills. No application at this moment. While we are on Rule 1, let's take a look at another one of these, because this one, of course, isn't as nice as the last one, because why would I be nice to you twice? 16. Is 16 a perfect cube? Because notice we have a cube root this time, so we would like to not have any perfect cubes under our cube root. 16 is not a perfect cube. Does 16 have any factors that are perfect cubes? Oh, yes, yes. As a matter of fact, it does. I can do the cube root of 8. 8's a perfect cube. 8's a factor of 16. So I can split the 16 into 8 times 2. So the cube root of 16 becomes the cube root of 8 times the cube root of 2, just like our property says. Again, I'm going to keep splitting this up. X to the 4th is not a perfect cube, but does it have a factor that's a perfect cube? Yeah, think about how we split up last time. I can go the cube root of x to the 3rd, because that is a perfect cube, right? And that's contained within x to the 4th. X cubed times x, we'd have a leftover x right here. So 8 times 2 is 16, and x cubed times x is x to the 4th. So I've just taken this and split it up using its factors, and I'm looking at simplifying the things that I can simplify. I can take the cube root of 8. I'm going to simplify that. I can take the cube root of x cubed. I'm going to simplify that. Ladies and gentlemen, once again, your words of wisdom. Do what you can do. Do not do what you cannot do. There you go. It can be as simple as that. I can take the cube root of 8. That's 2. I can take the cube root of x cubed. That's x. I cannot take the cube root of 2 or x. Therefore, I'm not going to. I'm going to simply put them back together again. Again, I've got the two separate factors. I'm combining them back into one. And what is stuck under that radical? What could I not get free? There's a 2 stuck there, and there's an x stuck there. That's it. That's the best that I can do to simplify this using my rules for simplifying radicals. So 2x times the cube root of 2x. Okay, now what? Well, there are actually 2 rules that we need to deal with, and the second rule says that we cannot have any radicals in our denominator. We haven't run into that yet because the first 2 examples did not have denominators. They were not fractions in and of themselves, so there we go. So let's make life more interesting, shall we? Of course, I think we should. Alright, so check this out. What are we looking at here? This is the 4th root this time of 16x to the 8th over 5. Great. Well, so maybe I start by taking things apart. Maybe I start with these guys here and seeing what I can separate. So the 4th root of 16. You know, I'm kind of liking that because 2 times 2 is 4, times 2 is 8, times 2 is 16. 16 is actually a perfect 4th, so I'm okay with separating that. That's okay. And as far as x to the 8th, if I think about that, that's got a perfect 4th in it. In fact, that's got another perfect 4th in it. So again, x to the 4th times x to the 4th is x to the 8th. So there's 2 perfect 4ths that are in there. Or power over root, we can see 2 of them. The thing that we're going to struggle with is our denominator. Because again, that radical applies top and bottom. So this is really the 4th root of 5. And here's the problem. I'm working right now and not leaving any perfect 4ths under my radical, but I'm not allowed to have this radical sitting in my denominator. And right now I can't take the 4th root of 5. It's not a thing. What can I do? What is the only thing that will undo a 4th root? Think about this. What will undo a fourth root? What's about to undo a fourth root right here? A fourth. A perfect fourth will undo a fourth root. 5 is not a perfect fourth. Can we make it one somehow? Can we engineer this so this will happen? Well, let's see. This is where I usually lose people, so pay attention. Times, what if I multiplied this times the fourth root of 5 cubed? Because 5 times 5 times 5 times 5 would be a perfect fourth. And that will allow me to get rid of this radical in my denominator. Is this legal? Not by itself, no. I have to multiply the same thing top and bottom. I don't want to change the value of the fraction, I just want to change its appearance. So if I'm going to multiply the bottom by the fourth root of 5 cubed, I'm also going to multiply the top times the fourth root of 5 cubed, multiplying same thing top and bottom. What does this do for me? Well, let's see here. Do I have space to put it here? I think I do. Yeah, I'm going to. All right, so equals. Do what you can do. Do not do what you cannot do. Can I take the fourth root of 16? Yes, I can. It's 2. Can I take the fourth root of x to the fourth? Yes, that's x. And that's another x, so x times x, that's x squared. So these are all the things that have been set free from the radical at this point in time. The last piece of the numerator, the fourth root of 5 cubed. 5 cubed is not a perfect fourth. I'm not going to be able to simplify that, so I'm not going to try. I'm going to leave it as is, the fourth root of 5 cubed. So times the fourth root of, I might not write 5 cubed though. What's 5 times 5 times 5? That's 125, yeah? Okay, so that's a lovely numerator right now. I like that. Well, what about my denominator? Because we are talking right now, I'm going to write something and then adjust it, so feel free to erase if you're writing in pencil here. Multiplying these together gives me the fourth root of 5 times 5 cubed, which is 5 to the fourth. Think about this. Fourth root of 5 to the fourth. Power over root. 4 over 4 is 1. What's happening here? My radical and my exponent are canceling each other out. What is going to be left? Ladies and gentlemen, just the 5. And now I no longer have a radical in my denominator, and I've got no perfect fourths under my fourth root. That is the best I can do right there for simplifying things. Okay, why did I choose a fourth root right here? Because I've seen people learn this, but they only learn it again with square roots. And so their first thought is automatically, well, if it's a 5, I'll multiply by a 5. Why does that work? Why will multiplying a 5 times a 5 get rid of a square root in the denominator? Because 5 times 5 is a perfect square. So do not work on autopilot. Actually think about these pieces parts here. All right? So I'm not going to just automatically multiply by the same thing unless I want to get rid of a square root. Okay, my point. Check out this next example, because to me it's important. This separates the men from the boys and the women from the girls and the people that understand from the people that don't understand. All right, so next one up. I'm going to leave this guy here, I think, because we can see, yeah, that's not bad. We can see our rules then. There we go. All right, so this one, again, if I'm trying to simplify, I don't want to leave any perfect thirds under my perfect cubes under my cube root, and I don't want to leave any radicals in my denominator. If you can't read this, this says the cube root of x to the 8th over 9. The cube root of x to the 8th over 9. All right, so let's start with what we did for the last one here and see if we can make this make sense. So, separate the things that are perfect cubes from the things that are not. Is x to the 8th a perfect cube? No. Does it contain one? Yes. Well, x cubed, that's a perfect cube. How many x cubes are going to fit next to the 8th? I can make another one. That's kind of nice. So that's x cubed, and that's x to the 6th. So I have 2 spare x's here. So I'm going to do the cube root of x squared. Again, just using our properties, separating things out here. All right, so we got this going on here. So things that I will be able to simplify, things that I will not be able to simplify. But that right there at least should take care of our first rule. Now, we have a 9 in the denominator. Have you watched the Matrix movies? I like the Matrix movies. When they finally learn to be able to see the code essentially and look at all those numbers and they see the numbers instead of seeing the people in the fake world that exists, watch the movie. This is how I look at these problems. When I see a 9, I don't actually see a 9. I think about it at its core values. I think about the numbers that make it up instead of just seeing it for face value. 9. What is 9? 9 is 3 squared. Why is this useful? This is insanely useful because if I have the cube root, again this cube root also applies to my 9. Some of you, after seeing this last one, would have said, okay, that's a 5, and I did 3 more 5s so that I would have 4 of them to make a perfect fourth. So some of you would look at this and go, well, I have a 9, and this is a cube root this time, so I'm going to multiply by 2 more 9s to make this happen. You can do that. It will work, but you will clean a bigger mess that you will have made for yourself, and it will take you longer. Think, understand, know what you're looking at. If 9 is really 3 squared, and I'm trying to make a perfect cube, I already have 3 times 3. What's missing? Just one more 3. So why would I multiply times 9 when I can just multiply times 3? Because 3 squared times 3 is going to be 3 cubed, which is going to fix my denominator issue. Again, whatever I do in the bottom, I have to multiply by the same thing on the top as well. So times the cube root of 3 on top. Again, not trying to change what the fraction it has for value, just trying to change its appearance. Do what you can do, do not do what you cannot do. I'm going to put this here. Okay, so we've got this. What can I do? I can take the cube root of x cubed. I can take the cube root of x. So that's x times x right there. That's going to be x squared. I cannot take the cube root of x squared. I cannot take the cube root of 3. So I'm going to, again, use my properties to put those back together again and call that the cube root of, well, x squared times 3. Usually we write that as 3x squared. That's a delightful numerator. What about my denominator? Well, I did 3 squared times 3. That's 3 cubed. So I'm taking the cube root of 3 cubed. The cube root of 3 cubed is 3. Again, you've got a third root and a third power. They are going to cancel each other out, leaving you with just the 3. Both of our rules are satisfied, and that is our simplified outcome. Right there. There we go. This, if you see what happened with this denominator, good. If you didn't see it, it doesn't make sense, please keep trying. It makes a ton of sense, and it saves you heartache, pain. Not everything is that complicated, of course. Let's look at this guy. This guy is much easier by comparison. He's scary looking. Oh no, whatever. But, again, just go with our properties. Why did I switch gears? Technically, I didn't switch gears. That's a radical. This is a radical. Remember, power over root. Technically, this is 7 to the 7/9. So this is 7 to the 7th power and the 9th root. However, it's written as an exponent right now because this is a lot easier for me to view as an exponent than it is as a radical at the moment. So I'm not going to see it as a radical. I'm just going to look at my properties. So yes, I'm multiplying. I've got the same base, different exponents. Where have I seen that? Oh, right there. Multiplying. Same base, different exponents. What do? I keep the base of 7 and I add the exponents. Some of you can't add fractions still. Rawr. Learn to add fractions. They have common denominators already and everything. So 7/9 plus 11/9 is going to be 18/9. 18/9. Hey, I know what that is. 18/9. 18 over 9 is 2. This is 7 squared. This happens to have a value of 49. Go me. So not nearly as bad as the last ones. One last example, then I promise to leave you alone. That's going to be this guy right here. And again, it is of a similar nature to what we are seeing in the previous. We are dividing. We have the exponential form going on right here. Instead of viewing them as radicals, we're viewing them as exponents, even though they are radicals. But I'm dividing. I have the same base. Ooh, dividing, same base. What am I going to do? Keep the base, keep the 16, and I'm going to subtract the exponents. So I need to do 3/4 minus 5/4. What is 3/4 minus 5/4? Again, common denominator. That's delightful. That's going to be negative 2/4, which is otherwise known as negative 1/2, which is otherwise known as, think about this. The last one went all the way down to 49. We can do this here, right? Think about what we have. All right, so we are talking, now I didn't put the negative exponent property here, but we have seen that before. What's a negative exponent? It is a reciprocal. So a negative exponent is a reciprocal, so I can work with that. And a 1/2 half power? Well, a 1/2 power is a square root. What is the square root of 16? 4. And the negative exponent is a reciprocal. This is 1/4. That's the final value, 1/4. Again, it turned to a fraction because the negative exponent is a reciprocal, so we flipped it over. And 1/2 power is a square root. Square root of 16 is 4. All right, this is just something that you learn by playing with it and experiencing it and looking at your properties. So please enjoy, practice. You got this. It'll happen.